Hi everybody, good morning. Before all, thank you so much to attend this lecture. As an extension of our International Congress of Research, I'm pleased to present the PhD Ahmed. Please give a strong clapping for him. Now, I will introduce him. Ahmed CHEMORI received his master and PhD degree both in automatic control from Polytechnic Institute of Grenoble, France, in 2001 and 2005 respectively. During the years 2004 and 2005, he has been a researcher and teaching assistant at Laboratoire des Synode Existent, ILS Central Supélec at University Paris 11. Then he joined Egypt's Salah Formelac as senior postdoctoral researcher. He is currently a tenured research scientist in automatic control and robotics for the French National Center for Scientific Research, CNRS, at the Montpellier Laboratory for Computer Science, Robotics and Microelectronics, LIRM. His research interests include nonlinear, adaptive and predictive control and their applications in robotics, underactuated, parallel robot, underwater robot, humanoid robot, and wearable robotics. He is the author of more than 95 scientific publications, including international journals, patent book chapters, and international conferences. He co-supervised 13 PhD theses, including 6 defended, and more than 35 master theses. He served as TPC, IPC member or associate editor for different international conferences, and he organized different scientific events. In 2017, he had been visiting Hwangson University of Science and Technology and China University of Petroleum as an invited professor. He has been invited plenary keynote speaker for various international conferences. Now, I will give the word to PhD Ahmed.
Okay, so thank you very much for this introduction and good morning everybody. So it is my pleasure here to be with you today. It's my second time here in Mexico and I will try to share with you my research activities during this week. So each day I will give a conference, a lecture on a subject. And let's today start with this first subject and in the end just tell me if it's interesting for you or no. So the title of my presentation, it concerns advanced control. So as you know, control, it means developing some algorithm for controlling one robot, for instance, to do motion, to do a task, to do something. So the idea of automatic control is to develop these advanced control techniques and to apply them for different kind of robots. Today, I will try to talk about the high-speed parallel kinematic manipulators, called also high-speed parallel robots, and I will introduce or focus the plenary or the lecture more on the challenges of controlling of this kind of robots, and I will focus also on the experimental results. So I will show you not the theoretical aspects only, but the experimental aspects, the application on real prototypes. And as you will see, we will have a very, very high-speed robots, and I hope that it will be a pleasure for you following my lecture. First of all, and to start, let me introduce myself first. So I come in from Montpellier, and Montpellier is situated here, as you can see on the map. It's a very nice city, situated in the south of France, the extreme south of France. Montpellier is known by many things. I will just focus on 2 things. First of all, you know, the oldest faculty of medicine situated in Europe is in Montpellier. So it was founded around 1220. And the second thing, which is very attractive also regarding Montpellier, according to the statistics, we have each year more than 300 sunny days. So we have a very nice weather in Montpellier. In Montpellier, we have different universities and we have different research labs. So I am coming from a laboratory called LIRM, and LIRM is coming from Laboratory of Informatics, robotics, and microelectronics of Montpellier. So this research lab has two institutions. So we have the University of Montpellier, and we have also the CNRS. So the University of Montpellier is easy, it's like your university. But the CNRS, I explain what is a CNRS. A CNRS is a research institution, and it's the biggest research institution in France. So it is a very big research institution which is present in many cities in France, and they have a huge number of labs in different kind of research. So biomechanics, biology, electronics, robotics, all the fields of research. This is why we call CNRS the biggest research institution. So our lab is situated in the north of the city, and here, as you can see, we have the two buildings of our lab, and we are in our lab more than 440 persons, including the permanent staff, it means the professors and the researchers, and also the PhD students and the administrative staff. Now, as the name indicates, the lab is organized in three departments. So the Department of Computer Science, which is the first one, and it is the biggest one in the lab. It's approximately the half of the lab. The Department of Robotics and the Department of Microelectronics. And as you know, through the lecture, I am in the Department of Robotics. Now, let me say 3 words about this Department of Robotics. So, we are organized in 5 research teams, and each research team is working on a subject of research in robotics. The first research team is called Dexter, and within the research team we are interested in control and design of manipulators for manipulation for 2 applications. So the first one is industrial robotics, and the second one is medical robotics. The second research team is called IDH, and IDH is coming from interactive, digital, human. And in this research team, the researchers are working on humanoid robotics and also its interaction with the human. As you can see here, an example of tasks that we can make with a collaboration between the human and the robot. The third one is ICAR, and in this research team, which is between the Department of Robotics and the Department of Computer Science, we are interested in vision. In vision in general, robotic vision, image processing, interaction, and so on. The fourth research team is called DEMAR, and in DEMAR, we are interested in the human sensory motor, so control, modeling, neuroprosthesis, and so on for elderly persons or disabled persons. The last research team is called EXPLORE. It's to explore the environment, so using mobile robots. So we have different kinds of mobile robots. We have underwater vehicles, we have classical wheeled mobile robots, and we have also aerial vehicles. So this is just the organization of the Department of Robotics. So now concerning me, I am in the first research team called Dexter, but I made many collaborations with the other research teams since I am working on control for different applications. So we can apply the controllers to mobile robots, underwater vehicles, exoskeletons, humanoid robots, and so on. This is why I am doing this collaboration with the other research teams. Now, our lab is known also by something which is very strong, it's the experiments. So we made different research in robotics, and we made all this research applied, experimented in different platforms. Actually, we have many robots in our lab. I will show you just a few of them to have an idea. So the first class is this kind of robots. It's parallel kinematic manipulators, or called also parallel robots. This is also parallel robots, but it's a cable-driven parallel robots, so it's different between this and this. I will be back on this kind of robots in this lecture. We have prototypes of mobile robots, manipulators. This is kind of serial manipulators, classical serial manipulators. We have surgical robots. We have under-actuated mechanical systems. We have humanoid robots, and we have underwater vehicles, and so on. Just to give you an idea. And these prototypes are inside this building. And in this lecture, I will focus my presentation on this kind of robots, parallel robots, and I will show by the end some examples of these cable-driven robots. Now, let me say a few words about my research. Actually, so I'm working in robot control or control of complex robotic systems with mainly 4 applications. First application is the control of under-actuated mechanical systems. There will be a lecture on this application during this week. The second application is parallel kinematic manipulators. It's the subject of this lecture. The third application, we have 2 things inside. So we have humanoid robots and we have also exoskeletons. So there will be also 2 lectures, one on humanoid robots and one on exoskeletons. And the last one, marine robotics or underwater robotics. And also there will be a lecture on this subject. So today let me focus my presentation on the control of parallel kinematic manipulator. Fine. So now we arrive to the subject of the lecture. And here, as you can see, is the outline of this lecture, the content. So I will try to introduce first the context of these parallel kinematic manipulators and the history. I will focus also on the control problem formulation. I will show you the experimental platforms. We have 2 kinds of experimental platforms, what we call redundantly actuated parallel manipulators and non-redundant parallel manipulators. And I will explain this concept, don't worry. The proposed control solutions, I will just list them. I will not detail them since we need some mathematics, some equations to understand everything, but I will not give details about this. I will not bother you with equations, don't worry. There will be no equation in the presentation. Now, then I will focus on real-time experiments. I will try to show you the final result. So you have a problem, you study the challenges, you design your controller, and you apply it. I will show you the final result, which results from the application of what you developed as a controller. So I will show different videos about the application of different controllers, and I will conclude the presentation by the end. Fine. First of all, and to start, let's understand first the history and the context of parallel kinematic manipulators. So the first thing to know, what is a parallel manipulator? Or they are also called PKM, coming from parallel kinematic manipulators. What is a parallel kinematic manipulators? Before introducing this definition, let me introduce the definition of a robotic arm. A robotic arm, we call them also serial manipulators. You know, they are like the human hand, the human arm. In the human arm, if you see the structure, so we have a sequence of joint, body, joint, body, joint, body, and so on, in a serial way. This is why the robot manipulators, we call them serial manipulators. Now, if you have understand this definition of robotic manipulators, let me introduce now parallel manipulator. It's very easy. Imagine that you have one arm and second arm, serial I mean, and you connect them together, like that. So, what you will obtain, it's a parallel, because you have one arm in parallel with another arm. So, this basics, it's a parallel kinematic manipulator. So you have at least 2 kinematic chains related to the end effector of the robot. Now, historically, if you see to the history of parallel robots, here I will show you some examples. 1931, it's the first idea of a parallel kinematic manipulator introduced by Gwinnett. In 1942, it was a painting system which is based on a parallel kinematic structure. And the first, and here for these 2 examples, it was just a patent. It's just a study. They have not built these parallel robots. The first parallel robot was designed in 1994. So this is the first one. It's, as you can see in the picture, here you have a wheel. It's the wheel of the car. So it's a system for tire testing, for testing the tire of the wheel of the car. See, this was the first parallel kinematic manipulator. And actually, as you can see here, there is an example. It's a flight simulator. It's the platform of Stewart, introduced in 1965. And initially, as you can see here on the video, the first examples of parallel robots, they have been used for flight simulators. So a flight simulator, you have seen it here on the video. So you have the cabin, and you have the pilot inside, and he tried to control the motion of the cabin, which represents the airplane, and we try by controlling the legs. I will just repeat the video. By controlling the legs here, as you can see, you can control the motion of the cabin to reproduce the same dynamics of a real airplane. So this is for the flight simulator, for training of the pilots. And then, as you can see here, we have also 6 legs. And the 6 legs are in parallel way. So we have 6 legs here, and we control the 6 legs to reproduce a motion of the cabin. 20 years after, it means in 1985, there has been a development of a new parallel manipulator, which is completely different from the previous ones using these legs as this one or in the video. This is what we call a lightweight parallel robot, which was introduced in 1985 in Switzerland at the EPFL. It's the Polytechnical School at EPFL in Switzerland, and it was introduced by Professor Clavel. I will show you a video to understand the origin of this lightweight parallel robots. And the robot is called Delta. It's called Delta, why? Because the form, as you can see here, it's like mathematical delta symbol. So it was in Switzerland, and here it was the first idea of designing a parallel robot for, as you can see here, it's a chocolate. So to put the chocolate in a box. This is the idea. So Professor Clavel had thought to introduce this kind of new robots, and the main idea inside his development, and he made a patent, the main idea is to construct what we call a lightweight parallel robot. What we mean by lightweight? It means that, as you can see here, the moving part, which is in the down here, it has a very low inertia and very low mass. So if you reduce the inertia and the mass, you can go fast. This is the idea. If you have something which is strong and very big mass, you cannot go very fast. But you have something which is not heavy, lightweight, you can go fast. So he tried to introduce this kind of robots, and at the first test, so it was not working, as you can see on the video. So then he tried to cut off and to think about what was the problem, why it was not working at that time for the first test of this parallel manipulator. And as you can see here in the video, he had an idea. And directly now he tried to go to the lab to try this new idea to modify the robot and to see what happened. So this is the life of a researcher. So even he's outside, he's all the time thinking about his research. And here, as you can see, this is the forearm. So he made here it's the arm and the forearm. So the forearm, it's made by 2 very lightweight pieces connected with springs, and it was working at that time. So this is the first lightweight parallel robot introduced in the world, and so it was introduced in 1985. So now, 20 years after, so this kind of robots now is becoming famous, and it is very well used in industry, and mainly, as you can see on the video, some examples, mainly they are using this kind of robots for food packaging. So food packaging, it means that you have some pieces arriving on a belt, for instance, and you try to take this object and put them in a box. And the idea is to do this task as fast as possible. So if you want to go fast, you have to reduce the inertia and the mass. This was the idea of Professor Clavel. And as you can see here, some typical examples of this robot made by Professor Clavel. So he made the patents, and then there have been different industries like Bosch, for instance. They bought the license and they produced this kind of robots for these examples of pick and place, as you can see on the video. Fine. Now let's introduce a parallel robot. So this is just a basic definition. As I said, a parallel robot has at least 2 kinematic chains, but it can be more. Here you have 4. It can be 2, 3, 4, 5, and even 6 kinematic chains. Some examples, the first examples of flight simulators. This is food packaging. This is a parallel robot for high precision positioning. The haptic interfaces. And now the main components are the fixed base, the traveling base, and also these components, so the arm and forearm. So a parallel manipulator is characterized by very high accelerations. So you can make motions with very high speeds and high acceleration. It is also characterized by high precision. It can go exactly to the desired value that you want, and it has a high stiffness, a high payload to the mass of the robot ratio. But the problem, it has small working space. It's smaller than a classical serial manipulator, because when you make it in a parallel way, you reduce the workspace. And the idea of my work regarding this application is to design some controllers to control the motion of these parallel robots for very high speed motions. So we have to pay attention of this problem, mechanical stops, for instance, and also we have to pay attention about the uncertainties, the actuation redundancy, I will explain it, and so on. Now, let me introduce the control problem formulation. Why we are interested in controlling of this kind of robots? Because for those who are learning control, you can take any controller and apply it. But the problem, classical controllers, they are not enough for this kind of applications. For the challenges and the problems related to this kind of robots that we will introduce here. So, first of all, I will show you these two videos, examples of real applications in industry for food packaging. So, the first example on the left, it's the robot of Professor Clavel. It's the Delta robot applied in industry. And the second one, it's here on the right. This one, it's the Quattro. And the Quattro robot is a robot that has been made in our lab in Montpellier. So just to show you these few examples from industry. And for all these examples, as you can see, the idea is to do what we call a pick and place task. Pick and place, you have some objects arriving on a belt, you pick the object and you place it in another place. Pick, place. And you repeat this operation, this task. This is the idea. So, if we are interested in control, we have to design controllers to do this kind of motions. So we suppose at the beginning that the end effector is here. Here you have the object that you want to pick. And here is the place where you have to place the object. So, pick, place. So, we have to define what we call a pick and place cycle. What is a pick and place cycle? It's a cycle starting from here. So we start from here, we move to the object, then we take the object and we move to the place position. We place the object, we go back to the initial position. This is one cycle, one pick and place cycle. So if you are interested to improve the speeds and the accelerations and to do this motion as fast as possible, you have to increase the speeds and the acceleration. So you have to design controllers that are able to do this motion as fast as possible. But pay attention, there is a problem. And you know the problem is coming from where? From this point and this point. This is what we call the stop points. Why? When you take the object, you have to stop. You take the object. And when you place the object, you have to stop to place the object. And between these two stop points, you have to accelerate at maximum. So even if you have a mechanical structure which is rigid, the fact that you have accelerated at maximum and you stop abruptly can generate this mechanical vibration. And also, we have to pay attention about mechanical vibration and the precision of motion, because this is necessary to do this kind of tasks. Now, we have to design controllers that are able to deal with these pick and place tasks. We have to generate some trajectories to do this motion. We have to track these trajectories using the proposed controller, while keeping in mind the problem of vibration. We have to reduce it either through the trajectories generation, either through the controller, the mechanical design, so we have different possibilities to reduce these mechanical vibrations. This is why we are interested in control of this kind of robots, and this is why if you put a classical PID, classical controller, it will not work perfectly. This justifies the control of this kind of robots. Now you can tell me, what about serial robots? Is it possible to use a robot manipulator to do the pick and place? The answer is yes. As you can see here, we can use, here as you can see we have two robots. We have, the first one here is the parallel, and behind it's a serial robot. It's a manipulator which has a serial. And if you compare like that, can you give me the amount of speed, the ratio between the parallel and the serial? The speed of parallel robots is equal to 2 times. Because, look, I will repeat the video. Look, the parallel robot, it takes 1 object at each time. And the serial robot takes 2 objects at each time. So it means the parallel robot needs the half of time to do the motion. So it has twice the speed of the serial robot. Anyway, now let me introduce the pick and place task. So the pick and place, as I explained, it's very easy. You have objects arriving on a belt. You take the object and you place it, and you go back to the initial position. To do this kind of tasks, we need either 2, 3, or 4 degrees of freedom. Do you understand what we mean by a degree of freedom? Look, you have an object in space. How many degrees of freedom it has? How many degrees of freedom? Huh? 1, 2, 3, 3, 3. So it has, look, this is one motion. This is 1 degree of freedom. This is 1 degree of freedom. 2. This is 1 degree of freedom. 3. It's enough? More. Nice. More. What we need more? An object can make a linear motion, but it can make another kind of motion, which is rotation. So the rotation, it's 1 degree of freedom also. He can do a rotation along X, along Y, and along Z. So it has 6 degrees of freedom. An object in the space can have maximum 6 degrees of freedom. Okay, so for the pick and place, we can need 2 degrees of freedom, or 3, or 4. I explained. Here for 2 degrees of freedom, you have objects. You have just to take the object to move along the Z-axis, the X-axis, and you put it. 2 degrees of freedom, like that. 3 degrees of freedom, either you need one rotation and 2 translations. So you can do this. Look, 1, 2, and you turn before you put it. So 3 degrees of freedom. And here also it can be 3 translations. You can do 1, 2, 3, and you put it. So 3 translations, or 2 translations and 1 rotation. And also we can need in sometimes 4 degrees of freedom. So you take the object, you do 1, 2, 3, and you turn before you put it. So you need 4 degrees of freedom. Now, so this is just the definition for the pick and place. If we look to the existing solutions in control of this kind of robots, we can find 2 classes. So the first one is the class of non-adaptive schemes. The second one is the class of adaptive schemes. Do you know the difference between adaptive and adaptive? It's very easy. If you know the PID controller, you have 3 gains: the proportional, derivative, and the integral. Okay? And you multiply these gains by the errors. The error, derivative of the error, the integral of the error, you compute the sum, and you have the control input. If you are in the case of non-adaptive, it means that your gains, Kp, Kd, Ki, so integral, derivative, and the proportional, they are constants. So they don't change. All the time they are the same. If you are in the case of adaptive schemes, it means that when you control your robot, these gains may be changed. So you have to find a way to tune them automatically. It's not you, it's the computer who will do this, who will tune automatically these values of the gains. This is what we call adaptive schemes. And now for non-adaptive schemes, we can find non-model-based and model-based. The difference between them, it means that the model-based, they use the information about the mathematical model of the robot. So you use the equation of the model of the robot. And the non-model-based, like the PID, as I said before, you don't need to know the model. You have just to compute the error, integral of the error, derivative of the error, you multiply by the gains, the sum, you obtain the control input. This is a not model-based. And model-based, like here, for instance, the computer torque, you use the dynamic model. And for the case of adaptive schemes also, you have non-model-based and model-based control schemes. Anyway, now before I will introduce the control solutions, let me show you our robots. So we have 6 kinds of robots here that I will introduce. And these kind of robots have been used to validate the proposed control solutions. So the first one is this one. It's a part 2, and it has this structure, as you can see, 2 actuators, and it is non-redundant. I explain also the principle of redundant or non-redundant. Very easy. Imagine that you have a robot manipulator which has 6 joints. 1, 2, 3, 4, and so on. 6. And in each joint you put an actuator, motor, asynchronous, DC motor, whatever. You obtain a robot with 6 degrees of freedom and 6 actuators. So this kind of robotic systems, we call it a fully actuated robot. Very easy. Now imagine that you have a robot and you have less actuators than degrees of freedom. It means that you decide to remove the actuator which is here, for instance. So you have 6 degrees of freedom and 5 motors only. This kind of systems, this is what we call under-actuated mechanical systems. But we have another case, it's the inverse of this one. So we have the case of fully actuated, number of actuators equal to the number of degrees of freedom. Under-actuated means less actuators than degrees of freedom. And the inverse, more actuators than degrees of freedom. So if we have 6 degrees of freedom motion, we can put 7 actuators. So we have 1 more actuator. This is what we call a redundantly actuated, or we can also call it over-actuated. It's exactly the same term. So the second robot is R4, and it's different from the previous one, since here we have 4 motors, not 2, but 4. And here the traveling plate, it can do X, Y, and Z. So 3 motions, 3 degrees of freedom, and 4 motors, so it's redundant. And here we have 2 motors and 2 degrees of freedom, X and Z, so it's non-redundant. Just this robot was patented, so we have designed this robot. It's a new design with the controller, and we made also a world record of maximum acceleration. So we made a patent of this robot from our lab. The next one is Velos robot, and you know R4, this one, and Velos, it's exactly the same structure. The only thing which is different, you know, the previous one, look here, I said that we have 3 degrees of freedom, so X, Y, and Z. Now, as I introduced before, from some pick and place task, we need to do this rotation. We do, for instance, this, and we turn before we put the object in the box. So we need this rotation. To introduce this rotation, look, this is the solution. So the traveling plates, previously, which was here, as you can see, 1 rigid body, it becomes 2 bodies. And this body is related to 2 motors, and the other body is related to the 2 other motors. And if you move one body with respect to the other one, we have a screw here, and you can generate this rotation. This robot has 4 degrees of freedom, and it's non-redundant. And the next one is the dual V. It has 1, 2, 3, 4 actuators, dispatched in this manner, different from the previous one. And it has arm for arm, and the traveling plate, which is in the middle. It has X, Y, and this rotation. So 3 degrees of freedom and 4 motors, so it's over-actuated or redundant. The next one is the Delta robot of Clavel from EPFL. So we made a collaboration with them to test our controllers and to compare. And the last one, it's the Arrow, which is different from the previous robots in a way that here, look, all the previous robots, they use a rotating motors. But here, they are not rotating motors. It's motors translating. This is what we call linear motors. This is a motor. It has 1, 2, 3, 1, 2, 3, 6 motors, and here it has 4 degrees of freedom, so it is redundantly actuated. The proposed control solutions, as I said, I will not detail them. You need a higher learning about control to understand all these controllers, but I will introduce just a list. And as you can see, I have emphasized one word, which is here in red, adaptive. We have designed different controllers, and as you can see, most of them, they are adaptive. And you know what's the reason? There is a reason behind this choice. Because we need a robust controller to avoid the vibration problem, but also we have supposed that when you take the object, we don't know the object. So we don't know the mass and the inertia of the object. So what we will do in real time, so the robot will take the object. When the robot takes the object, in real time he will estimate his mass and his inertia. And he will use this information in the controller. So you can use this kind of controllers to take whatever the object that you want to take. 100 grams, 200 grams, 300 grams, not a problem. Because the controller is here to adapt himself. And we have applied to all these platforms, so these 6 prototypes. And now I will show you the final results. So what we have obtained as a result of application of this different kind of controllers. First, so the first test was on this robot called Part 2. And Part 2, I have introduced this previously, I will recall it here. So it's to do the pick and place of 700 millimeters, 25 millimeter height, take an object and put it and repeat the motion. So it has 2 active arms and 2 passive arms, 1 rigid platform. And here, this is the traveling plate, and it has only 35 grams. We try to reduce the mass and the inertia of the moving parts. This is the idea. And we have the possibility to use this or this or this. We have chosen this serial structure, and here, as you can see, the 2 arms in red are actuated by the actuators in blue. And the 2 others, it's just to prevent the motion in the other plane. If you do pick and place in this plane, we don't need to move in this plane. This is why we add the passive arms. So we tried with different accelerations, 20G, so it's 0.35 seconds, the cycle time, 30G, 28 cycle time, 40G, so 23 seconds, and the maximum it was 50G. G is the gravity. So if I said 50G, it means you have a maximum linear acceleration of 500 meters per second square. And this is the final result. We can compare 10G with 50G, and you can see the difference between them. So this test was done just in the lab. So it's not real application industry, but it's enough to use this robot in industry to get this acceleration of 50G. The same robot we have tested here in this game. As you can see, he will play with these 3 balls. At the moment, just 1. And then he will accelerate because he needs to manipulate 2. And then we will ask him to manipulate 3. And so it has to accelerate more. So here is just to show another application for this high-speed parallel robot called Part 2. Nice. Now we tried, so this was within a research project, and after that we made another research project called, you know, the name of the project is called Objective 100G. G, as I said before, is the acceleration. It's approximately 10. It means that we want to get an acceleration of 100G. It means an acceleration of 1,000 meters per second square as a maximum linear acceleration. And I will show you the results. So we tried actually with 30G. So this is the first one. And we tried with 40G. And as you can see here, we can see the difference between 30G and 40G. It's a pick and place of, look here, this is the 40G. And this is the 30G. You can see the difference between them. So this is the first test using this robot called R4. And here we repeat the same scenario with 200 grams of a payload. And we can repeat this video, please. This one, and then we can compare, so with the difference between 30 and 40G. We can see already the difference between them. Now, as I said before, the objective is to get to 100G of maximum acceleration, and I will show you the video of 100G. But before, let me show you this video, please. And this video, the trajectory is here. So it's circular motion until we get to the maximum acceleration. I think it was 40G. And then we stop the robot, we go back to the initial position, we stop the position of the robot. So this was with 40G. and now 100G. So 100G, before we, to understand, so if you have here a vehicle with 100G of maximum acceleration, so in 1 second, you will reach 3,600 kilometers per hour. We made this motion, so we increase the amplitude and the speed and acceleration until we reach 100G, and then we reduce to go back to 0. And as you can see, the camera was not able to follow the motion of the robot. So, and this was a world record of maximum acceleration, 100G. So we made this record using this robot R4. I will show you other results. Here, as you can see, it's the Delta robot at EPFL it's the travel robot, Delta. We made this 3D pick and place task with and without payload. Here, actually, we put the payload. We suppose that we don't know the value of the payload, and the controller was able to adapt himself to control the robot. So we compare the nominal case and the robustness test. And here, as you can see, the curves for the nominal case, so we improve by 42% the precision of tracking of the reference trajectories. Between these two cases, the original nonlinear controller and the adaptive one. So if you add an adaptation, you improve the precision of the controller by 42%. Here, I told you that we suppose we don't know the mass of the object. Look, we are estimating, and we convert to 200 grams. So the object was of 200 grams. In real time, we can have an estimation of the right value. And here it's the tracking errors, and if you add the adaptation, you can improve by 62% the precision of the trajectories tracking. And what we did also, we did with and without payload. If you add the payload, so we can here identify the value of the added value of the payload. Another result here is on this robot called GeoV. Here, as you can see, we have the trajectories. This is the moving platform, and we try to follow these trajectories. And we do also two cases, the nominal case, and we try to add a payload that we fix it on the traveling plate here, and we can see this is the payload. It's around 1 kilogram perhaps. I don't remember the value, but we repeat and we compare both cases, and we try to see that the controller is robust to this modification of the payload. And here, as you can see, the curves, we can improve by 35%. Here, the estimation of the mass and the inertia of the traveling plate. And then, when we add the payload, we can improve by 53%. And we can identify here the difference of with and without payload. The difference is here estimated in real time. Another example is here the Velos robot. As I told you, we need this rotation. Look here to the motion. We try to follow the trajectories here in red. And as you can see here, we have a rotation. Here, when it stops, we can create this rotation. So we try to follow these trajectories. So this is the result on this Velos robot. And now the curves of this scenario, an improvement of 68% between the case of the original L1 adaptive control and the L1 adaptive control with feed forward. So we try to do an extension of this control to improve it. And we improve the precision by 68%. Here we have the control inputs. It's the torques applied on the motors. And here you have the estimated parameters of this controller. Now I will show you a video of the robot called Arrow with linear actuators. Look, the linear actuators, they move in linear way. This is the traveling plate. And the idea of this robot, you know, it's not the pick and place. The idea is to do machining. I will show you another video to see exactly what is the machining. And the traveling plate here, it has X, Y, Z, and one rotation around Z, so 4 degrees of freedom, and 6 actuators, so it is over-actuated or redundant. Now, we have an improvement of 79% comparing so the L1 adaptive controller and the same control with feed forward. And we have a precision of 7.4 micrometer in the space. So Previously, I told you that our objective was to reach 100 g of maximum acceleration. And in that project, we didn't look to the precision. The idea is just to go fast, 100 g, and that's all. Whatever the precision is, it's okay. But here, we tried to do two constraints. We have to go fast, not 100 g, but 10 g, 10 or 20, and we try to reduce the precision until a value less than 20 micrometer. So we get around 10 g of maximum acceleration and 7.4 micrometer of precision in the space. And this is why we said that parallel robots are more precise than serial robots. Here just the curves of the estimation of the parameters, and I will show you a real scenario of the machining. So this robot, it was designed finally to do this kind of motion. So you have the traveling plate, and on the traveling plate you have the tool. You control the position of the tool, and here it's the piece that you want to machine, and you can control this rotation. We have a motor here to control this rotation. And this is the final piece. It's like a pyramid. This is why we try to use this robot to do machining of this kind of pieces. Now I will show you just two examples. Another example, it's here an adaptive control also. This is a cable-driven robot. Just a question, do you know cable-driven robots or no? Have you an idea? I expect, yes, very nice. What is a cable robot? What is a cable robot? Do you know in stadium, when you look to a match of football, sometimes you look to the player and the camera is close to the player. You know the idea what is? The camera is here, they use cables, they fix the cables there, and the camera is here, and we control a motor to pull cables, and when you pull the cables, you can move the camera. So in real time, the player is running, and the camera is moving near him. So this is the idea of cable robots. And why we develop them? Because previously, if you have, pay attention, for parallel robots, I said that if you have a serial manipulator, a robotic arm, you have this space. If you make two, you reduce the space, because you cannot do this. You do like that. You cannot go until here. So you reduce the space. The idea of cable robots is to increase the workspace. So you have not used rigid bodies, just cables, and the platform is here, and you control the platform to move in this space, big space. So in this case, we have applied our controller, which is the Geospace L1 adaptive controller, on this robot, which is huge. Look here the size, 15 meters by 11 meters. 11 meters by 15 meters. And we try to control the motion of this robot by controlling the motors. And you know the challenge of controlling this kind of robots, you know what is the problem? A rigid manipulator, you can, using the actuator, you can push or pull, because it's rigid. The cables, you cannot do both. A cable, you can just pull, you cannot push, because you have to keep tension of the cables. Here, perhaps you cannot see clearly the cables. They are fixed there, and we can choose also the structure. 2 cables, 3 cables, 4 cables, 6 cables, until 6 cables. So number of actuators equal to degrees of freedom. If you put 8 cables, you obtain more actuators than degrees of freedom. So it's become redundant. And this is just an example. So we can move just some masses here, around 100 kilograms or more, by controlling the motion of this platform. And we made another application, the same structure, but the application is different. The application, it's like the previous applications. So it's a pick and place, and we have this robot that was designed by Tecnalia. Tecnalia is a company from Spain, and they have also in Montpellier, place there. They are working in parallel robots also. And in this research project, they developed this robot called P-Cable. So you will see it's with cables, but it's smaller. And the idea is to do the pick and place. Here, look at the cable. And you control here the motor to pull the cable to move the traveling plate. This is the traveling plate, and this is the pick and place task. And you know the advantage of this kind of structure? Whatever your place in your company, you have just to choose, I put the molder here, I attach the cable there, and there, and there, and there. If the structure changes, it's smaller, I will put the cable here, and there, and there, and there. And I can change very easily the structure to do the pick and place task. And here, as you can see, the different characteristics of this robot developed by Technalia, and for different applications up to 4 degrees of freedom of pick and place tasks. And I arrived to the conclusion. So during this lecture, I tried to share with you this application of control on which I have worked recently. So we are interested in control of parallel kinematic manipulators. This kind of robots, as I said, they have very high accelerations. They have 2 cases, either redundant and non-redundant, or overactuated and non-overactuated. And we measure only the positions of the motors. We have to deal with some challenging problems if you are interested in control. The problems are high nonlinear dynamics. The mathematical model is highly nonlinear. The operation conditions may change, so you take an object, you don't know if it has 100 grams or 200 grams. So you don't know this, so it may change the conditions of work. Actuation redundancy, I explained it. Real-time constraints, and the problem of mechanical vibrations that we have to manage when we design our controller. So I have not developed the controllers, I have not detailed them, but we developed different adaptive controllers, and we try to implement them, for sure in simulation just to start, but the most important for me is the real-time experiments on these experimental platforms. And I have shown you one experiment of 50G maximum acceleration and the other one for 100G. And also I have shown you one application with very high precision, 7.4 micrometer of maximum precision. And to finish, I will give you just some information. This is just the link to my web page. Just in Google, you put the name, you can find the link. If you want, if you are interested in the details of the controllers, the technical part, the equations, how we compute them, how we apply them, you can download the papers from this website. It's ResearchGate. And then, if you want to see more videos about this kind of robot and others, you have just to put my name in YouTube or Google. You can find this YouTube channel. So it's called Robot Control, and inside you can find 60 videos of all the experiments. I give you my email address. If you need any information, you can contact me. And to finish, I thank you very much for your attention.
Thank you so much, Ahmed. So, someone had a question? That means that everybody here is nobody? No questions. Jonathan has a question.
What kind of application can be developed the duality robot?
Very nice. Okay, very nice question. Let me go back. I can show you. It's very nice question. He understands because the previous robots. Let me go back. So for the robots where we are interested in pick and place, most of them are interested in pick and place. Fine. So for this one, it's the pick and place, food packaging. This one, it's the same. This one, it's the same, pick and place. This one, the question is regarding this one.
Yes.
This one is not for pick and place. And it's a very good question. You know, the application where we can use this robot is laser cutting. Laser cutting, it means you put a material, you put the head that will generate the laser beam, and you control the motion of this laser beam to cut this metal. And the idea is to put here the laser beam. And then you control the motors to move in a precise way to have shape. And you put here the metal that you want to cut. And then you can have very high precision of cutting. This is the a typical application of this robot. Other questions?
I have a question. In my case, I work with adaptive control. I showed you to use more of different scale for deal with it. In this case, you know that for adaptive control, you must attend the persistent station. So, how to deal with it?
Very good question, but I think it's somehow technical. But I can explain. Let me go to the proposed control solution here. You know, here the question is very good, since if you look to some of these controllers, he talked about the persistence of excitation. What is this concept? I explained. You want to track some reference trajectories, so you want to follow this motion and repeat it. This trajectory, it should be able to excite the parameters that you want to estimate. I want to estimate the mass of this body that you want to move. If I do a simple motion like that, perhaps I will not excite enough the parameters. It means what? It means that I cannot guarantee that this, yes, I cannot guarantee this. I cannot converge to the right value. So I need to pay attention to the persistence of excitation of the parameters. So we made two kinds of controllers. The first one, it's like this one, for instance, and the idea is just to work on the trajectories. When we generate the reference trajectories, we use polynomials, and we try to choose these polynomials with the right frequency and the right trajectory to excite enough the trajectories. But this is the first solution. The second solution, I have not developed the detail of the controller, but let me just tell you a few words. This one. This one is called L1 adaptive control. And you know, L1 adaptive control was developed to avoid exactly three problems of classical adaptive control. The problem of persistent excitation. In L1 adaptive control, you don't need excitation. It's okay. Very simple trajectories, it will work. One. The second, performance. The previous controllers, as I said, let me go back here. If we start with a value far from the real value, maybe we cannot converge to the right value. So we have to pay attention. We need an initial knowledge or a priori knowledge about the parameter. I want to estimate the mass of this object, but I know previously that it is between 100 and 200 grams. I need this information. Otherwise, it will not work. So the idea of developing L1 adaptive control, so we forget about this information, we suppose that we don't know anything, and we start from zero. So we can start from zero the trajectories, and we can guarantee the convergence. We start from zero and we converge. So this is the second point. And the third point of the L1 adaptive control with respect to the classical adaptive control is that classical adaptive control, you know, I showed you this convergence for the previous case for the classical adaptive control. Here, look, we have, when we design the control, we have a parameter. It is called the adaptation gain. If you want to converge quickly, and it's better for you, if you converge quickly, it means that you have the error, it will converge like that. So the error will be just from here to here, not from here until here, until 25 seconds. So you want to converge quickly, you have to increase this parameter, the adaptation gain. And the problem with the classical control, if you increase enough, you may generate vibrations. This is the problem. But with the L1 adaptive control, there is no limit. You can increase your gain. The only limit is the hardware. Otherwise, not a problem. So for this controller, L1 adaptive control, you increase and you can go fast and you will be never unstable. You will be all the time stable. So this is the three advantages of the L1 adaptive control with the classical adaptive control. Other questions?
Thank you.
Yes, please, go ahead.
We can use the robot arrow.
So?
When can we use the robot arrow?
For the robot arrow, I have shown the video. Perhaps you don't pay attention. Look, this is the application. Your question is about application, where we can use it? When? We have finished it 2 years ago. So we have finished around 2015, 2016. And we take approximately 1 year and a half to construct it, because we have the mechanical design, we have to buy the different parts, the actuators, and we have to machine the pieces and so on. We have to assemble everything and to design the controller. So it takes 1 year, 1 year and a half to construct it. The purpose is machining. If you want to do a piece, you can use this for machining. This is just to illustrate the concept, but the real application, if you have any piece you want to fabricate it, so you can use it. You put just the initial big piece, and then you can do this machining to fabricate your desired piece. The precision. Yes, the precision here, I gave the value 7.4 micrometer in X and Y and Z. So you can have very good machining with a maximum error of 7.4 micrometer of precision in the space. Position in space. Other questions? Yes.
What kind of motors are used in Delta robots?
Very nice. Very nice question. Now a question about the motors. All the robots, they have motors. And now what kind of motors? So if I go back, here I will show you. Look here, or even I can go back to show you the robot and they can give details. Yes. So actually in this robot we have used brushless asynchronous, so it's brushless motors here, coming from Etel. Etel is manufactured in Switzerland. So they are very powerful, 127 Newton meter, the maximum torque. So they are very powerful. Here it's the same as you can see, the black parts, it's the same. The Delta here, it's direct drive, asynchronous motors also, direct drive. And here the last one, it's linear motors, coming from Etel also. Other questions or remarks or comments? No? What do you think? It was clear, or you understand the meaning of the lecture? Huh? What do you think? It was okay? Or? Huh? You are learning English. Okay. Sorry, I cannot speak Spanish. Otherwise, I can do the presentation in Spanish. But
thank you so much again. Por favor, le damos otro fuerte aplauso al doctor Ahmed. Bueno, aprovecho para hablarles rápido en español. Para los estudiantes, el doctor Ahmed va a estar con nosotros todo lo que resta de la semana. Cada día de la semana va a dar una plática acerca de sus temas de investigación. Mañana hablará de su tema de investigación, control adaptable de pequeños vehículos submarinos, de los experimentos, perdón. Bueno, el título en inglés es Adaptive Control of Small Settled Autonomous Underwater Vehicles. Control adaptable de pequeños vehículos autónomos submarinos. Entonces, por favor, si quieren saber el título de la presentación del miércoles, pues aquí los esperamos mañana. Entonces, de nuevo le damos un fuerte aplauso.
Universidad Politécnica de Tulancingo. Líderes construyendo su futuro.